was born in Hull in Yorkshire in 1939, just before the Second World War, and except for maybe 3 years in Wales with my grandparents, I spent all my school years in Hull. I got into chemistry because I happened to be good in science, and in Britain you get streamed very early. And so I was streamed into maths, physics and chemistry, and I happened to be good in chemistry. And went to King's College in the University of Durham, and as a make-up subject I had to take an additional science, and I happened to pick geology. And that sort of got me bitten by geology, and whereas I went in to do honors chemistry, I ended up doing a joint honors degree in chemistry and geology. Geology is interesting in those days in that I didn't just get the mineralogy side of it, but essentially I was trained as a geologist: paleontology, stratigraphy, mineralogy, petrology, etc. And when I finished my BS degree there, I decided I would like to get into geochemistry in a real way. And there were very few places, probably no place in Britain that was particularly good at that time outside of the exploration geochemistry area. So I applied to Penn State and got a graduate assistantship with two people called Johns and Burnham, looking at pegmatite petrogenesis. And basically that's where I got interested in synthesis of minerals, genesis of minerals. I suppose I was much more orientated towards the chemistry side rather than the geochemistry side, and after doing a master's degree there I went back to Britain and joined Professor Barra's group at Imperial College and did a doctorate in zeolite chemistry at Imperial with Barra. There we worked mainly on the absorption and encapsulation of gases in various zeolites. The main objective there was to find a model encapsulating system for helium that one could then put in fuel rods in atomic reactors, and the release of helium after heating up the trapped gas in the zeolite would essentially act as a signal indicator on a mass spec on the reactor, indicating if any fuel rods leaked. That got me into zeolites, it got me into adsorption, diffusion, encapsulation. And when I left, or decided I was going to leave Britain in 1967, before I left Penn State, I'd married a very attractive Pennsylvanian young lady. We decided to return to the States. I joined W.R. Grace and Company in Columbia, Maryland. Went to work for a carrier called P.K. Marr in zeolite synthesis. And there I became involved not just in zeolite and catalyst synthesis, but also in materials for absorption and separation of hydrocarbons, purification of gases, things of that nature. Very much involved in promoters for catalytic cracking, new promoters, particularly looking for alternate catalytic and promoter systems in FCC. And of course, when the oil crisis hit in '73, we became very concerned about ways of converting heavy crude oil, very large molecules, selectively into gasoline and diesel fuel. Do you want to cut that off?
Hello? Yes. Yes, how are you? We were going to be here at the hotel at 7:30. I'm not sure. A person from work and a person from SRI would be glad to have you. Yes. No. Okay, and in the Meridian, in the lobby. Okay. All right.
You got a conversation too. Anyway, our main objective was to find materials that had pores bigger than zeolites that would give us selective conversion of heavy crudes. The first thing we turned to were amorphous materials. And during that period we synthesized a series of materials that we called VK3 that were synthesized in zeolite-like hydrothermal systems in vanadium, potassium, aluminosilicate systems. These turned out to have very narrow pore size distributions in the range of about 20 to 30 angstroms. Catalytically, they were essentially as active as zeolites, and they had the very high desirable selectivities for the heavier ends. One problem with them was that with all small pore amorphous materials, they tend to have very low steam stability. However, they were super hydrocracking catalysts in the sense that they yielded very high diesel fractions. But the key was it was a demonstration of the fact that small pores, whether they be structured or unstructured, small relative to the molecule you're probing it with, have a high activity. Essentially, you need not just an active site, but you need a constrained environment, or an environment that perturbs the molecule in a way that enhances the site activity. After that work was winding down, the idea was still to seek alternate materials that had small pores, but were not of the 12 ring type you get in zeolites, that is limited by about 8 angstroms. We decided that the range of maybe 15 to 20 would be optimum for heavy crude conversion. And I was at a Gordon conference in, I would guess, 73, 74. And Camille Clear gave a talk on amino acid separation on phlogopite. And basically that talk triggered the link between sheets and large molecules that resulted in the idea that if we could put inorganic pillars between the sheets of a clay, controlled by the species of polymer we used, then we would be able to develop a cracking catalyst system that would first of all be ordered, it would be controlled, but most importantly it would have pore sizes hopefully much bigger than those in zeolites. And the result were pillared clays. We limited ourselves strictly to those oxide systems that we knew were useful, or certainly not detrimental in cat cracking. Phosphorus, boron, aluminum, zirconium, titanium, silica. And when you look at the solution chemistry of those systems, you find that in fact only aluminum, zirconium, and titanium really form, or what people believed formed, very large cationic polymeric cations. And of course clays are cation exchangers. The view was that if we could exchange these into the clay, we'd get the order and therefore hopefully the stability that we lacked in the amorphous systems. The result was that we focused on aluminum chlorohydrol, the Al13 Kagan ion. It has very nice solution chemistry. It's very accessible with various probes, particularly X-rays. And we ended up basically with a large pore system, marginally larger than the conventional zeolites. In looking at zirconium, we found that we could get much larger pores. In fact, pores more in the range of, rather than 8 or 9 angstroms as we did with aluminum pillars, maybe twice that in some cases. Zirconium also had the advantage of being more stable. And basically we built on those two discoveries. Titanium, of course, tends to precipitate at relatively low pHs, in which one may destroy the clay. So we spent very little time on titanium, but later on it's been amply demonstrated in the last year or so that in fact you can pillar with titanium too. But we focused on modifying aluminum pillars to make them highly stable and highly active in the cat cracking, in the hydrocracking processes. These we took through a series of inventions involving, first of all, building bigger pillars to make them more stable, and hopefully building in more activity by reacting the pillars with things like silica, so that one might have a silica alumina pillar. Unfortunately, a whole series of steps with pillared clays ran parallel with a series of steps in cat cracking that ended up making the process much more severe. The riser cracking, the attempt to burn coke more selectively at higher temperatures resulted in the need for increasingly stable materials. And whereas the pillared clays were very good potential cracking catalysts for 1975, 1976, they failed what we would call very severe standard steaming conditions in 1978, 1980. However, they, at that time and still do, offer a lot of potential in both hydrocracking and a variety of petrochemical processes. What we see since 1980 is a whole series of people moving into the field and pushing it forward at a fairly rapid pace. The Chinese here have certainly been the most successful with the pillaring of a double sheet material called rectorite, where they can maintain very high stability. In looking at pillared clays, one has to consider not just the pillar but also the sheet. I think we took things to the point where the pillar was as stable as the sheet, and the sheet fell apart at high temperature. What the Chinese have done essentially is develop a sheet pillar system in which both are very stable. And it's going to be very interesting to see how these develop in an industrial sense. But again, these are the results of very, very massive efforts. At Grace, basically it was a two-man effort. And for probably most of the time between 1975 and 1979, it was essentially two of us spending a third of our time on it. What we see now is a massive effort in China, significant effort in Japan, and a much broader effort in the United States. And this kind of resource focus is bound to bring a whole series of new catalysts in both petroleum and petrochemicals. It's an area that continues to be very exciting as different people come in with different kinds of pillaring, different compounds for pillaring, the possibility of different sheets, the recognition that there's a whole range of positively layered sheet materials, of which hydrotalcite is the simplest, brucite being one end member of it, magnesium hydroxide, but into which one can substitute a whole variety of transition elements. These are amenable to anion exchange. And in this case, we have accessible an enormous number of transition metal Kagan ions. These are quite difficult to intercalate. It can be intercalated, and as people focus more resources on the techniques and the species, then I think we'll see a whole variety of new metal catalysts coming out of the development of this pillaring concept.
Was that a major activity of yours at Grace, or was this something that you and the other person did on the side?
It was a major activity from the concept that probably we developed in '74. We got immediate funding for it, and it was a major program for both of us in 1974, 1975. Our focus was invariably both synthesis and catalysis. And during this time, we pulled in Professor George Brindley at Penn State to try and help us with some of the characterization. He became much more involved in the synthesis too, and he sort of went off track somewhat. But he did some very interesting synthesis work too. It sort of duplicated and paralleled what we did, and it turned out not to be that interesting to us. What we had hoped is that he would solve the problems of how the pillar connects to the sheet. And I think he concluded he couldn't do it, so he went off and did something else.
Well, that was one of my questions. How did you characterize these first clays to convince yourself it was?
The focus of the characterization was X-ray diffraction, of course. It was what was known of the solution chemistry of the system, and the NMR, the aluminum NMR, had pretty well nailed the solution species as far as we were concerned. And the AL13 species being commercially available was a relatively easy thing to make and purchase and use. And this allowed us to make fairly large quantities of material fairly rapidly, or at very early stages of the program. But pore size distribution was crucial, as was hydrocarbon adsorption, which gave us a molecular probe of the kinds of channels and cavities that we had in the system. But those were the essential physical indirect methods that we used in association with the fact that the layer spacing matched almost exactly the solution chemistry of the K-gonine we were feeding into the layers. The absorption capacity matched again pretty well what we would expect from a saturation layering of the layer structures. We were convinced at the very early stage that we'd done what we had targeted. When it gets to zirconium chemistry, the zirconium chemistry is much more complex. And even now there is very little solution work that has been done on the species of zirconium in solution. We concluded again very early that the low spacing, 18 angstrom spacing zirconium materials were pillared with a square planar ZR4 complex that was described by Clearfield and Vaughan some years before. Not my Vaughan, another one. And so that too fitted the theory very well, and again, the absorption capacity matched pretty well what we expected, and probe molecule experiments confirmed that. It became more complex when we made the larger spacing zirconium materials that had spacings of about 21.5 and 25.5 angstrom spacings. And here we decided the simple way to view this was to view it as a cross-sheet stacking of these zirconium-4 polymers to essentially give us bigger pillars. One can rationalize that quite well if one considers a double stack or a double complex of ZO4 giving you again an 18 angstrom spacing. But if you stack 3, you can go to 21.5. You stack 4, you go to 25. So it seemed reasonable that in fact what we were seeing was a series of zirconium polymers in solution. And in many systems what you ended up with were mixed spacings, indicating that the polymer solution comprised several polymers in solution. And they tended to intercalate individually into layers, so that one would get one layer that pulled in an 18 angstrom spacing, and another low would pull in a 21.5 angstrom spacing. This, I think, was reasonable considering the kind of solution chemistry we're involved in. But this is zirconium chemistry is a great opportunity as far as I'm concerned. Nobody seems willing to tackle it.
Where did you first report this work on?
Well, our main concern was, of course, getting a series of patents issued that developed the primary concept, and then 2 other patents that were concerned mainly with stabilizing the clay in different ways. We developed particular ideas as to why the clay was decomposing. The first idea we had was that if the pillars migrate in steam, then if we make bigger pillars or less reactive pillars by reacting them with silica, the silica alumina being less reactive in steam, they'll hold up longer, and this turned out to be true. That was the second patent that we issued. Our conclusion on the sheet metastability was triggered by the fact that on decomposition of the large Kagan iron to the oxide pillar, one sees a significant loss in exchange capacity of the clay. One also sees a dehydroxylation of the clay at a much lower temperature than one sees in the untreated clay. And we concluded that during the decomposition of the Kagan iron to the pillar, that the protons released during this process migrated to the octahedral layer in the clay, resulting in essentially protonic self-destruction of the clay itself. By calcining in ammonia, or by immediately exchanging with other cations, we essentially captured those protons and prevented that migration and self-destruction of the octahedral layer. That too resulted in much higher stabilities, and that was the third patent we issued. At that point, we decided that essentially the stability problems, or the lack of stability problems, in our steaming experiments convinced us that we could not go very much further with these materials, and that they would not compete with zeolite commercial cracking catalysts. And essentially it was at that point that we decided we would publish. It was also at that point that the patents started issuing. First one in 79, and then 80. And our first publication on this was in 1980. But the patents contain a tremendous amount of data, of course. The initial publication, of course, created a lot of excitement as it was published in the zeolite community. And a number of people immediately recognized the possibilities. Among them, I think, Jan Utteroven, who was, of course, a zeolite and a clay person. And Pripyat, too, who immediately saw the applications into areas where they had a great deal of expertise.
Did you meet any skepticism within the company after you decided that you hadn't been able to make this?
Well, there's always skepticism in any company. The fact that when one sets up a research project, one sets up certain targets. And the fact that your salespeople keep coming in and changing those targets, as far as they're concerned, is immaterial. You immediately forget the initial targets. The fact that you met those targets becomes somewhat irrelevant if somebody has given you a new target. And so, certainly within the company, I think there was very little recognition at the time. These, in fact, were important discoveries and important developments from a catalytic viewpoint. The other problem with Grace is that it tends to be a one-product company, in the sense that they're massive in cracking catalysts, and that dominates everything else. And although these were obviously good hydrocracking catalysts, or could be good hydrocracking catalysts, just as VK3 was a very good hydrocracking catalyst, they had no business in hydrocracking, and therefore they were not interested in it. It's a strange myopicity that many commercial people tend to have. and Grace, to some degree, is a one-product company in the catalyst area, with very little interest in trying to spread the focus elsewhere. Obviously, there are a lot of good petrochemical opportunities with these materials. The possibility of putting transition metals into the clay structure, and as Shell has shown, bleeding out those into the interlayer as metal colloids or small metal clusters, gives you a unique kind of catalyst kind of system. But Grace was merely interested in cracking, and anything that didn't fit into that they were not interested in pursuing. And so we essentially dropped the project in, I would guess, early '79. Except for patent work, it was really dropped in probably late '78. But the need to supply data to the patent office has kept it moving into about early '79.
And where was the first place you presented this swirling? Was that?
This was in Naples, in I suppose it was the 5th International Zeolite Conference in Naples, which was a strange meeting because it was it was organized in a manner the Italians called a reporter system. And so papers were clustered and presented by one person, and then people answered questions on those materials. It was really later that people began to, who had a knowledge of clays, like the Belgians, who jumped on it and tended to look at it in a much harder manner. It was interesting to the clay community. Brindley published before us. We were confronted at an early stage of Brindley wanting to publish, and us not wanting to wave the invention around so that a lot of other people would jump in on it. We'd funded some postdoc research with him, and of course we couldn't hold him up too long. So, in fact, he published in about 1978, I think. But it was very fine print that said it was supported by Grace, and no one seemed to notice that. And so the full realization of the potential, I don't think, was recognized until our patents started to issue. And the first patents gave a lot of cracking data that clearly showed these things had very high cracking activity under mild steaming conditions. And indeed, they approach the activity of zeolites. Because of the larger pores, they tend to cut deeper into the heavy ends, and the products tend to be heavier too, which is what you'd expect in a larger pore kind of structure. You don't crack the molecules down as much, and you can eat up more of the larger molecules. And so you not only cut into the heavy ends, but you created very good yields of light cycle oil, diesel fuels, which at the time were very much in demand, and probably still are a major objective of cracking catalyst synthesizers. Light cycle oil catalysts, or demand for them, comes and goes. And as the less industrialized countries become more reliant on FCC, their demand will very often be orientated towards light cycle oil. Cat cracking is much cheaper than hydrocracking, and if they can get light cycle oil from cat cracking, then that's the way they should go.
Well, you're in an ideal situation to compare U.S. and English graduate schools. What are the similarities and the differences?
Penn State, to me, when I first went, was somewhat of a shock, in the sense that when you finish a degree in Britain, a graduate degree basically is research, or was research in those days. I came to Penn State and I found I had to start taking courses again. And there was an element of argument and rebellion there that working in essentially an area of material science, it was a different kind of orientation of the chemistry I'd done. And basically, my period at Penn State focused a lot of my ideas as to where I wanted to go. It was very useful to me. But a graduate student coming from Britain to the US is coming into an entirely different kind of system. I would say that there are advantages and disadvantages to both systems. The British graduate with a BS is far more advanced in his science than is the American. The stuff that Americans do in the first 2 years of undergraduate work, and I've got kids doing this at the moment, is stuff that should have been done in high school. And so the first 2 years of an American university education is an education that shouldn't be in a university. And in Britain it isn't. However, when you get to the PhD level, in Britain, still in most universities, graduate students don't take many courses. There are very few universities that require significant levels of courses. There are a few of the departments at Imperial College that did require graduate students to take a low level of advanced courses given to them, but even there weren't very many. This means that when someone finishes with a PhD in the States, they've certainly caught up in basic knowledge with a British counterpart, and very often they've had a pretty good research experience in addition. I think the main difference is the British graduate student probably is trained to be more creative than the American one, which from a viewpoint of invention is very important. From the viewpoint of basic knowledge, they probably end up in a very similar spot. In looking at recent graduates of both systems that I'm associated with, it's very difficult to say where you prefer to make your choice. They still have both strengths. They're different. And I think the difference is that I would say the British PhD is generally more creative and often less broad in his total knowledge. The American student is broader in his total knowledge, but often his creativity has been very suppressed by the system in which he's been brought up. I think in many cases the American graduate system is not one that stimulates creativity, but tends to suppress it. Even at graduate level, I was amazed at the requirements of professors for pat answers, straight book responses, rather than trying to get people to think differently and come up with alternates. And science, after all, is in fact cut and dried only at a very low level. The deeper you get into something, the more complex it is, and the more questionable you have to become. But you don't, I think, get that in most American graduate schools. I think it's a fairly big problem. So there's a combination of both systems that I would like to see. I suppose what I'm saying is the American graduate school would be great if, in fact, the professors would be less oppressive and less concerned with people following a line, often their own, and being more self-expressive. But the other thing you have to remember is that even now, European graduate schools or European universities in general take a much smaller proportion of their students than American universities do. Probably you have more people in graduate school here than you, as a percentage of population, than you have in undergraduate schools in many European countries.
How did Barra direct graduate students? Hands off, or was he?
No, Barra's technique of management is a very interesting one. He's an individual who is enormously enthusiastic about the work he does and did, and he's very impatient for results. Even though he was head of the chemistry department, and the chemistry department at Imperial was 3 or 4 Nobel Prize winners and a couple of other people, Chain, Wilkinson, Barton, Tompkins, Barr himself. So he was not only involved in that management level and keeping those people from cutting their throats in many regards, but he'd dispose of most of his administrative duties in the morning, and he'd be bugging his students in the afternoon. He used to visit at least once a day. Sometimes it'd be around twice a day. And the question was always the same: anything new? And there are some people who can say, yes, this is what it is, this is what I think it might mean, and he'd discuss it and debate it. And, he was someone one could argue with, but I must admit, I don't think I ever won an argument with him. A brilliant physical chemist. Very, very methodical. Tremendous teacher, because he would sit down with you time and again and go through the same thing in a very methodical manner. If he'd been through it 3 times before, it didn't matter, he'd do it again. But this kind of pressure upset quite a lot of people, and a number of people seemed to be driven crazy by it. He would have a particular round of visiting his graduate students, and people would say, oh, he's 2 labs down, I'm going for coffee. And they'd disappear for an hour until he'd gone past his station, so to speak. But again, if you didn't object to that and took it basically with the spirit in which he pursued it, I don't think he intentionally was putting the whip on people. He's too nice a person to do that. But he is enthusiastic. He was eager for information. And I think that is basically what still drives him. He's still writing books. He's still intensely interested in the science. He still gives lots of papers, even though he's in his mid-70s. He's still very active in the subject, and he gets very excited over new discoveries. And so it was this that drove him, and basically that drove a lot of other people. But he had a lot of good students. I had a lot of very good colleagues.
And how many students would he have at the time you were there?
Oh, I would guess that he essentially had 3 main areas. He was interested in synthesis. He was interested in absorption and diffusion over a wide range of materials, and he was very much interested in membranes. I would guess when I was there, he probably had about, between 12 and 15 students. He was the kind of person that you'd write a paper or a draft of a paper and spend maybe 2 or 3 weeks over it and hand it to him, and you'd have it back the next morning. Or you'd hand him a thesis draft and you'd have it back the next morning. He just never set things aside. He did them instantly. And so he stayed on top of everything. And obviously he must have delegated very well to both his secretary, and he had an administrative assistant to look after a lot of the course organization and the physical organization of the college. And he delegated a lot of that stuff, and he stayed up with the science and led the science, and in many regards continues to lead the science, not just in zeolites, but also in diffusion, and still retains a significant interest in membrane science.
Well, what did he do outside of science? What sort of a person was he?
Well, a lot of his personality in science is I suppose, reflected in some of his outside activities too. But his main interest was tennis. He was a tennis blue at Cambridge. He was also a running blue at Cambridge. But his tennis stayed with him, and it was very rare he went around without a tennis racket if he saw the opportunity for a game. During the Wimbledon couple of weeks, he was never in the lab. That was off. He just took that whole period off, and still remains a very avid, keen tennis player. He used to stay with us a lot and still does when he consults with both Grace and Exxon. And turns out that he was a tremendous table tennis player also. My kids used to fancy themselves in this sport of kings. And he took great pleasure in absolutely whipping them. He's the cocksure young guy. And they'd always go away shaking their heads and say, well, next year he's going to be a year older and he's going to be slower. And I'll get him then. They haven't yet. Very keen competitor. Very keen competitor.
How did he approach zeolite science?
Very methodically in the way he does many other things. But I think he missed his important error in the zeolite science was in tending to stay with the geochemical approach to zeolites. The major break in zeolite synthesis came when the people at Union Carbide essentially discovered that low temperature reaction, the kinds of things that chemists tend to think about as moderate reaction conditions, ambient to 100 degrees in the lab, when they recognized and demonstrated that in fact you can make zeolites under what a geochemist or what previously people would have said absurdly mild conditions. He missed that. He was very productive in the higher temperatures. He tended to focus on what I would call mild geochemical conditions between 150 or 180 and say 300 degrees centigrade, which is from a mineralogical viewpoint of zeolite synthesis are probably the mild end of the conditions that you would view as being reasonable. At that time, no one was aware of these massive deposits of zeolites that essentially formed in lake beds, large parts of the western states, Wyoming, Nevada, Arizona, California. Here you have very large deposits of ground ash that was thrown out from the big volcanoes of Northern California, Washington, and Oregon, covering large areas of those states. Essentially, those reacted to very diverse zeolite groups at relatively low temperatures, probably in the range of maybe 40 to 60 centigrade, in what amount to salt lakes or very mild aqueous weathering conditions. Those were unknown until probably the mid to late 50s, and probably were the key to some of the work that Carbide did, or should have been the trigger for them to recognize that much lower reaction conditions were feasible. But these weren't recognized until relatively late in the zeolite synthesis era, at least as far as Barrow was concerned.
So he did his at high temperature, high pressure? He
did his at high temperature, but autogenous pressure, which means at 200 degrees, I think water vapor pressure is maybe 15 to 20 atmospheres. So they were not the kilobar pressures that geochemists tend to play with. My work at Penn State was done mainly at pressures between 2 and 10 kilobars. Zeolite synthesis, as done by Barrow, was probably never much more than 100 atmospheres.
Well, did this geology training make you a rock hound?
Not a rock hound in the gem sense, but one of the advantages in working at Grace was that, like Union Carbide and other people, they were very concerned about the potential competition from natural zeolites. After all, you can go out to Arizona and you can take a bulldozer across an acre and you can rip up tens of tons of rock very, very cheaply. no pollution problems, no need for plant. All you need is a bulldozer and a truck. And most zeolite manufacturing companies have had at the back of their mind that someday somebody would find a zeolite deposit that might put them out of business. And in fact, there were a number of applications, particularly in sour natural gas and ion exchange, particularly cesium ion exchange for radioactive cesium, where there was a market for natural zeolites. It was small, but over many years it was steady. So when I was at Grace, I used to get a couple of weeks in the field every year, either looking for areas that might throw up a new zeolite deposit, or evaluating a deposit that someone was trying to sell us, or just characterizing a deposit that we owned. And that was a lot of fun. So from that viewpoint, yes, I was somewhat of a rock hound, and I still have a strong interest in natural zeolites, the petrogenesis, the synthesis techniques of trying to match various natural deposits. But I'm not one of these avid collectors that you would normally associate with a rock hound who every spurred moment he goes chasing rocks. I'm not, that's not my bag. But in terms of looking at synthesis, and in looking at natural zeolites as being very valid sources of zeolites for experimentation, I have a very strong interest in the natural materials.
How did you get involved in the Zeolite Society?
Well, the first Zeolite Society meeting, the International Zeolite Association, the first meeting was held in London, and it was run by Barrett. And of course, I was still working for Barrett at the time. In fact, it was the year that, it's 1967, it was the year that I decided I was going to come back to the States. And essentially the International Zeolite Association started at that point, and as these meetings have been essentially massive outpourings of data and information on zeolites every 3 years, then I've remained, I have attended all the meetings. For anybody involved in zeolites, they're very, very important meetings to be at, because of the people who go there and the literal enormous amount of information that comes out at those meetings. Scientifically, that they are very, very important meetings. And so I've continued to have a fairly avid supporting role in pushing these as a major educational vehicle in the zeolite field. The next one is, the last one in Tokyo was probably the most impressive one. We thought the one that we organized ourselves, John Ward and I, a union organized in Reno, was an impressive conference, but the one in Tokyo was topped it in terms of the level of the organization and the output of the program. The next one in Holland, I think, will probably be a somewhat lower key meeting. But nevertheless, the field is moving very, very fast. It's expanding. It's not just becoming more intensive in terms of the amount of knowledge we are now able to get from a lot of these spectacular techniques that have begun to come to fruition in the last 4 or 5 years, which give us a much deeper understanding of zeolites. Things like high-resolution electron microscopy, things like NMR, not just silicon, but aluminum, phosphorus, oxygen, tracing cations, sodium, lithium, and so on. The depth of our understanding of zeolites is now so much greater than it was just 2 or 3 years ago. Even the impact on such intensively researched areas as cat cracking. And this meeting we've been to here is one where clearly NMR is having an immediate impact on our understanding of octane catalysts. All this is very intensive, makes the field very, very exciting, pulls in a lot of new people. But at the same time, we have this enormous expansion of the field into areas of the periodic table that 2 years ago we wouldn't have thought or dreamed possible. The metal aluminophosphates is one example of that. So from the viewpoint of opportunity in new materials, there's an enormous amount of action. And that, again, brings people to the honeypot, so to speak, brings in new ideas, brings in different people from different backgrounds. And this, again, intensifies the understanding of zeolite. It's now expanding more than it ever has. The big efforts the Chinese are making, the big efforts the Japanese are making, all these are relatively new. And so the number of new materials is seemingly expanding exponentially. The number of patents issued a year is well over 1,000, probably topping close to 1,500. It's one of those rather unique areas where one has not only an intensifying academic interest, which incidentally is still mainly outside of the United States, but an enormous industrial interest where industry is pumping up the fundamental science as well as the applied science. People talk about superconductors being exciting, but industrially, zeolites is where the action is. Superconductors still can't offer us converting 20 million barrels a day over zeolites. This is an enormous commercial area. The sad thing I find is the lack of support in American universities, and still there is no American university that I would say is an international rank in zeolite chemistry. There's no one to compare with Leuven, for instance, or the Japanese centers, or various Russian centers, or Imperial College in London, or there just isn't the focus or the support. And that I find very unfortunate, because the industrial interest here could generate the backing to create one. There just doesn't seem to be the spark. Good.